So if you're just getting started with microcontrollers, sooner or later you're going to run into devices that you want to control that use the I2C protocol. And it's nothing to be intimidated about because it's very easy. It's only two wires off of your microcontroller that you connect all of these I2C devices to. So it's a bus. So you can connect all these devices to those same two wires where the microcontroller is the master and all of the devices are the slave, so that the master actually controls when it wants its data and when it's going to write data to the slave devices. It's only two wires, and in fact it's a lot of times called a TWI interface, or two-wire interface, and they market it as a really simple, easy to use two-wire interface. And I've done plenty of tutorials on how to work with I2C. These are devices like an EEPROM or a DS1307 real-time clock or a compass, anything. There's a million devices out there that use I2C. And I've done tutorials on how to communicate with these devices, but I'm always using a microcontroller, and I'm always using a library within the microcontroller to talk to these devices. But then I'm starting to think, actually I got a question on my YouTube channel about how to bit-bang I2C. So what I mean by bit-banging is writing bits high and low on the clock and data lines to talk to the devices. But then I'm starting to think about it, well, I don't have to bit-bang it. I could actually physically control an I2C using buttons, push buttons. So what I have set up here is an EEPROM. This is a 24LC256 EEPROM, and in case you don't know what that is, it's a memory chip. It's a non-volatile memory chip that stores bytes of data even when you lose power. So you write data to it, and then you can cycle power for like 100 years. You can be powered off, bring your power back on, and your data is still there. Okay. So anyway, what I have set up here is an EEPROM, and then I have a whole setup so that I can pull the data and clock lines low via these push buttons. So when I push the push button in, it pulls either one of those lines low. So what we're going to do is physically bit-bang an I2C device, and this will be really helpful. It's more of an experiment to see how I2C works, because when you're using the library, you don't really know what's going on in the background. But here I'm going to show you exactly what happens when you write and read data from an EEPROM. Okay, and then towards the end of this video, I'll show you the schematic of what's going on here in case you actually want to replicate this circuit that I have here. This is going to be very painful to watch because this is a 256K memory chip, so that means that the addresses require 2 bytes of data, and then you have the actual data that you want to store, which is a byte. So it's kind of it's going to be a little heavy to watch this one. So let's get started, and I'll explain how this works as I go. Okay, so before we get started, let's talk a little bit about what's going on here. So we are going to be the master in this I2C bus. And what I mean by that is we control the clock via a push button here. Actually, we can control the data line as well. But the way I2C works is you have a master that controls the clock. So from the master, the clock is output only, and to all the slave devices, the clock is input only. Whereas the data line, well, and what I've got here is this top button here, and this LED correspond to the clock line, the bottom button and LED correspond to the data line. The data line is bidirectional, meaning that the slave or the master can control it. And they're not really driving this. So both of the data and clock lines are pulled up high via 10K ohm resistors. And either device, the master or any of the slave devices, pull these lines low. Well, they only pull down the data line, really, because that's the one that's bidirectional. So if I wanted to control the data line, I simply push this button in. And in my case, what I'm doing is driving a transistor that pulls the line low. And same thing with the clock. But the point is that the slave device does not control the clock line. I control the clock line, which is why we're able to conduct this experiment. Because if the device controlled the clock, then there's no way we could see these things happen very slowly. So since I'm controlling the clock, we can go as slow as we want and see the data go in and out of the bus. And trust me, this will all make sense as we move through this. It's going to be kind of painful because, you know, we're clocking in bytes and bytes of data here with push buttons. So it's easy to screw this up, and I probably will screw this up, so bear with me here. So let's just go ahead and get started. So right now we have an EEPROM hooked up to this. Both lines, data and clock, are sitting here high, which is normal. So this is when no communication is occurring. Both lines will be high. To initiate the start command, the master will pull the data line low while the clock line is still high. Okay, so if we did that right now, this initiates a start command. Right now, the device, all of the devices on the I2C device wake up, and now they're waiting to see what I'm going to do next. Because the next 7 bits define the device address. If those 7 bits match the device, then the device acknowledges that and will do whatever you want it to do. So if I'm going to write data to or read data from it, that will occur right after the acknowledge. And this will make sense as I go along here. To stop data communication, you go from a low to a high on the data line. So right now, that's a stop command. And you can do that anytime during the transmission and everything resets, okay? And this is true for the EEPROM. I've looked at some of the other data sheets. They're all kind of the same kind of thing, but after you write the device address and the data you write to and from the device, that depends on the device, on what you're doing with it. But in this case, it's very simple, straightforward I2C stuff. And it does have to be in a protocol. This is always the same for all of the I2C devices, because otherwise they couldn't sell the devices, because you connect all of these to the same 2 wires, okay? So even if I had other devices here, they would all have to follow this same protocol. So let's initiate the start command and let's start writing stuff to it. Or actually, what we'll do first is we'll write a few bits to address 0 of the device. Okay, so that's what we're going to do first. We're going to do a byte write. I don't know what we're going to write. Maybe we'll write like a 4 to device address. We'll write it a 4 to this device at address 0. Okay, because this is a 256K memory chip, so you have to tell it which of address in the chip you want to write your byte to. Okay, anyway, start command. Now we'll pull the clock low. Now the next 7 bits we write into it are the device address. There's 4 bits that are hard-coded, and these are 1010. So let's write in a 1, write in a 0, write in a 1, write in a 0. The next 3 bits are the wired address bits. So this device has 3 pins that you can tie either high or low, and then that will set up the next 3 bits here. So I have them all tied to ground, so they would be all 0, 0, 0. So we'll write 0, 0, 0. Okay, so now this device is woken up. Now we have to tell it what we want to do. Do we want to write or read to it? If we want to write to it, we simply write a 0 next. Okay, if we were to read, we would pull this line high and then write a 1, but we're going to write a 0. And everything's on the rising edge, so I can play with this and nothing is happening right now. It's only when I rise this clock up or let it, pull it back up to 5 volts that it'll actually register what I have on the data line. So let's go ahead and write a 0. And then I'm going to let go of the data line. Look, I let go of the data line, but now I'm not pulling it low. The device is pulling it low. This is the acknowledge bit. Okay, so following the start command and then the 7 bits of address followed by the write bit, which I wrote a 0 to, it acknowledges it. So the device now knows I'm talking to it. Okay, I'm going to write in the acknowledge bit, and now it gave me control back. So if you look at the data sheet, the next thing it wants now is the address, the memory address, and it consists of 2 bytes, an upper byte and a lower byte, okay? The high byte, the low byte, because it's 256K, so you need 2 bytes to represent the memory address. And we're going to write to address 0 because it's easy, okay, and that way we don't screw up. So I'm going to pull the data line low, and I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. And then look, the device takes over and acknowledges it that we've got the high byte in, okay? Clock the acknowledge in, it gave it back to me. Now we're going to clock in the low byte address, memory address. 1, 2, 3, 4, 5, 6, 7, 8. Let go of the data. The device is now taking control, giving me the acknowledge bit. Clock in the acknowledge bit. See, normally we're looking at this. We're looking at the LEDs to see what it's doing. Normally these are connected to the microcontroller, the master. So it's writing and reading at the same time this data line. So it knows what's going on, you know. So it's looking for that acknowledge bit to be pulled low. And it's all built into the chip. It's all built into that library. So this is just to demonstrate how everything's actually working in slow motion. Okay, so now what's next? We clocked in the acknowledge bit. So we clocked in the high byte, the low byte, and we've seen the acknowledge bit. Now we're going to clock in the data, the actual data we want to write to it. So what we'll do is write, I don't know how to do this. Maybe we'll go, let's actually make the bit 8 of the byte, or the bit, well, actually it's bit 7 if you want to count bit 0 as the first one. So the highest bit in the byte, we're going to make a 1. And then we're going to make it a, so that's 1, 0, 2, 3, 4, 5, 6. We'll make that a 1, 7. Okay, all right, that was the last one. So anyway, see how it's kind of hard to do this with push buttons, especially while I've got one eye on the data sheet here. But we just wrote a byte to memory address 0. It gave me the acknowledge bit. Now what I'm going to do is I can clock in. I'm going to clock in the acknowledge bit, and then it gave me control. But now what we have to do is give it a stop command. Okay, so I have the clock in. So what we'll do is I'm going to hold this in as if we're clocking in a 0. I'm going to clock in a 0 now, and then I'm going to let go of the data line. So anytime you move the data line while the clock line is high, it's going to give it either a start command or a stop command. So in this case, when the data line is going from a 0 to a 1, while the clock line is high, it gives it a stop command. So we just did that. So it just clocked in that goofy, whatever byte I just wrote to it, it just wrote it to memory. Okay, so we just wrote a byte to memory address 0 of this device. Hopefully that makes some sense. Probably not the easiest thing to follow in the world, but anyway, here it is. So, okay, now that's how you write a byte. Now here's the problem with this device. In order to read a byte out, you need to first write to it, okay? Because right now we just wrote to address 0, memory address 0, and it automatically incremented the address to the next address. At least that's how I'm following the data sheet. So what we need to do if we want to read back from that address, we need to first write to it, but we're going to write to the high byte, which was all zeros, then the low byte, which were all zeros. And then right before we write to the byte in that address, we're going to bail out of the communication. And when you do that, it freezes the address where you're at. And then you can do a byte read immediately. And when you do the read, it reads from the last address accessed. Okay, so let's go ahead and do that. And this kind of demonstrates how you would do that anyway. So what we have to do is first write to the device. As if we're writing to it, then we write the high byte, the low byte, we bail, and then we do a read from the device. So it's kind of a lot of steps here, but we'll do it quickly. So we initiate the start command, 1, 0, 1, 0, and then the 3 zeros, 1, 2, 3, and then we're going to do a write, so we keep it hot or keep it low. Get the acknowledge, we got the acknowledge, clock in the acknowledge. Now we write the high byte. 1, 2, 3, 4, 5, 6, 7, 8. We got the acknowledge, gives us control back. Hold that low, and we go 1, 2, 3, 4, 5, 6, 7, 8. get the acknowledge, we've got it back. Now what we're going to do is bail on this as soon as it gives us it back. So now we've got it back, but what we're going to do is let go of the clock line. We're in the current address. Normally what we would do here would be to write the byte information to this memory address. What we're going to do is bail out on it, and we're going to initiate another start command. So we're at the current address. It's going to freeze that current address. We're going to do another start command and communicate back with it. So we're going to go 1, 0, 1, 0, and then the 3 zeros, 1, 2, 3. And then this time, instead of writing, we're going to read. So we bring that up. Now watch this. This is kind of cool. As soon as it clocks in the read command, it's going to give us the acknowledge right back. So we do that. Now my next cycle down, boom, there's my acknowledge. So the device took over and pulled the line low. Now I don't have control over this. It's a byte read. So the next 8 cycles are going to be the data information that it's getting back. Okay? So I think I wrote a 1 to byte address 1. There it is, the 1. So that's if we're just going to go down 1, 2, 3, 4, 5, 6, 7, 8, and then the acknowledge, and we're done. So now we're out. Okay? So that's what we just read. We just read that byte of information from that memory address. So that's pretty much it. And if I kept going here, I believe you can do like page writes and page reads where you just keep reading. So like right now we could just keep reading from the next address. So we just read from memory address 0, but we could keep going 0, then we could go to 1, then we can go to 2, 3, 4. But I should have acknowledged. I think I was supposed to do, it's called a sequential read. But I should have acknowledged the slave that I received the byte, and then it would have went on to the next memory address. But right now, things are the bus is stable, so there's no communication. Okay, so that's how it works. That's I2C. Hopefully that made some sense to bit-bang it with the switches here. Now let's talk a little bit about this schematic in case you want to play with this, because you could do quite a bit with this. Or maybe you don't want to use push buttons, but you could use a microcontroller to just demonstrate it in a very slow fashion how things are going. The only problem with a microcontroller, though, is once you get into an acknowledge, it's kind of hard to tell who is pulling it low, who's pulling the data line low. So when you get those acknowledge bits, was the microcontroller doing it or was I doing it? It's kind of hard to follow those sort of things. I guess it's pretty easy to do in code, but I'm just saying it for this sake, it's pretty clear that I'm not pulling it low, so the slave device must be. All right, so let's bust out the schematic for this thing. Let's go to the whiteboard and see how that looks. Okay, just before I go to the schematic and draw that up, I want to show you this data sheet, and just because it might make a little bit more sense to see some of these timing diagrams in here. Before I go too far with this, because I did sort of fly through that a little bit. So here's the data sheet for the 24LC256. You can see here we have max clock frequencies, but there's no minimum because we are controlling the clock. The master controls the clock. There's no minimum clock. There's no calculation time. There's nothing. So we can go as slow as we want, but obviously there's a max clock because of input capacitances and voltage sweeping, and there's characteristics of the input to this chip that there's limitations on. So if we keep going down here, let me show you these. Yeah, there's so much I can show you in here, but let me swing through here. So here's a bus timing data. We don't need that. This breaks down all of the pins on the chip, but I want to show you here. Here we go. So here's data transfer sequence on the serial bus. And you'll see here's the start condition. So that was when the clock is high, we pulled the data line low, and that initiated a start condition. And then you can see here we go through address or acknowledge, valid, data allowed to change. If we keep going through here, I just want to show you, here's the stop condition. So the way I initiated the stop condition was I went in with a 0 on the rising edge of the clock, and then while I held the data line low, when the clock was high, I pulled the data line high, and that initiated a stop condition. Down here you can see the acknowledge bit. So you can see the slave device pulls the line low, and then you should clock that in, and then it lets go of the data line for you to control. Okay, so here is the way it works. Let me go to just one that makes sense here, a write operation. So here's a byte write. Here's your start bit. Here's the hard-coded 1010, and then here's the 3 addressable pins. We made all zeros. So we went 1010, 000, and then since you're writing, you follow that up with a 0. Then you get your acknowledge, and then you write your high byte, you get your acknowledge, you write your low byte, your acknowledge, then you write your data, get your acknowledge, then you stop. Okay? Let me show you one more thing here. A read. They call it a random read when you want to read from any address in the chip. And you can see here what it's doing. You do your start command, and then you do your control, what they call the control byte. Same thing, followed up with a 0, which will write to it. You get your acknowledge, your high, your acknowledge, your low, your acknowledge. Then you bail on it. Instead of writing data to it, you initiate another start command, and then your control byte again. But look, this time it says 1 there instead of a 0. And this will read from the chip now. Get your acknowledge, and immediately you'll get the data from this address. Okay? And then you follow that up with a stop. So you can do that there, or you can do this sequential read where you get your data here. I'm not sure if you acknowledge it. So I didn't do a sequential read, but I'm wondering if you should be this acknowledge. I'm not sure who it does. Yeah, so the master issues the acknowledge as opposed to a stop condition used in a random read. Okay, so these are the kinds of things that, if you were to play with this, you'd figure out. So if you're doing a sequential read, does the master give the acknowledge here, or does the slave do the acknowledge? And it's pretty clear that, see right here, you don't get an acknowledge. It'll immediately let go of the line, and it's waiting for you to acknowledge the slave device like it's showing here. And then it will automatically increment the address so you can just keep reading data out of it. Okay, so anyway, that's kind of, I wanted to go over the data sheet a little bit here, and we could probably dig into this a lot more, but this video probably already is too long. So let's show you what the schematic looks like. Okay, so here's the circuit minus the LED monitoring circuit. Okay, so this is just the buttons controlling the clock and data line, and I'll add the LEDs in as we go. I just didn't want to complicate this too much. It probably already looks kind of crazy, but it really isn't too bad. So let's just go through what we've got here. Here's the actual memory chip. If we go right through the pins here, A0, 1, and 2 are the configurable address pins. I have them all tied to ground so that it is 0, 0, 0. Ground pin obviously is tied to ground. VCC up to 5 volts. The write protect pin is left floating since it has an internal pull down. If we tied this to 5 volts, the chip would be read only, so we wouldn't be able to write data to it. Here is SCL and SDA. This is the clock and data lines. So if you go out here on the clock lines, I have both of them pulled up to 5 volts with a 10K ohm resistor. And then on the other end, they're connected to the collectors here of these 2N3904 NPN transistors. So they're just connected to collectors here, which means that when we turn this push button or push the button in, we will be putting 5 volts on through this 1K ohm resistor connected to the base. And then on the emitter here, we're tied to ground. So when we push the button in, it will saturate this transistor and sink current down through the collector to emitter, pulling the line low. Okay, so right now, when the buttons are open like that, both clock and data lines will be pulled up high, and then whenever you push the buttons in, that pulls the lines low. Okay? So that's how the whole circuit works. It's pretty simple. The clock line here is input only on the chip, like I was telling you. So it's monitoring whether this is high or low. The data line has the ability to also pull the line low. So inside here, it's not only monitoring it, so it probably looks something like this. It's got like a buffer which feeds in, and it's monitoring this whether it's high or low, but it also has the ability, there's probably some kind of tap off here, it also has the equivalent of an NPN transistor where it can also bring the line low, okay? It's actually an open drain output, so you might have heard of open collector outputs. That's like when you have a BJT type output like this. So the collector is open and you're just pulling it low like that. In this case, it's an open drain. It's just using a MOSFET to pull it low. But anyway, I don't want to confuse that too much. The point is that the chip has the ability to also pull it low. And this might, when you first look at this and you're controlling it, bit banging it, your first instinct might be like to think that you could damage the chip if two devices are both controlling it at the same time. What happens if they both try to pull the pin low? Like, what if I pull it low and the device pulls it low? Well, if you think about it, nothing will happen, right? Because if you look at the current path, so if you say this was, if I had the data line, this push button pushed in, pulling the data line low, and the device was trying to pull it low, you can see that there is no damage that could occur. So current would be flowing through here, but then if the device also wanted to pull it low, it would be nothing but just another ground path. Okay, so it really wouldn't do any damage to it. It's not like I'm driving if I was driving the line high and low, so if it didn't have these pull-ups here, and I was able to drive it high and drive it low, then you could have some damage there. Like if I was trying to drive it really high and this was driving it low, then you would have a dead short, something like that. But that's not the case with I2C, because all of the devices on the data line are just going to sync the line low, okay, since you have these pull-ups. I'm kind of going off on a tangent here, so hopefully you guys are still with me. But anyway, so that is the circuit. A few extra things I added in here. So you want to watch out for bouncing. If you are going to build this circuit using buttons, when you push the button in, it is a mechanical action, so you're going to get bouncing, some jitter on that. So I put little 0.1 microfarad capacitors right here to ground on both of these lines. Okay, like that. And that minimizes the bounce on it, so that there's a nice, instead of like something like that on your rising and falling edges, it's more of a nice gradual rise and fall on the lines, so that helps a little bit with that. If you watch my video on the shift registers where I use buttons to control it, you'll know what I'm talking about here. Okay, so that's the circuit, but then I added in this LED monitoring thing, which looks something kind of like this. So I'm going to draw it. Hopefully you'll be able to see it. I'm going to draw this quickly. We have a 1K to a, hopefully you can see that. And then we have the LED here. 5 volts. Okay, so what we have here, if you can see that whole circuit, is we have a 100K ohm resistor connected to a base of a 2N3904 NPN transistor. This is connected right up to one of the lines. Okay, so when this line is high, it drives this 100K ohm resistor through this transistor, saturates the transistor so that we have an LED with a current limiting resistor up there connected to 5 volts, so that the 5 volts, then you have current flow through this path to light the LED when this line is high. Okay, so it completes the path. And the reason I had to do this with the high impedance 100K ohm versus the 10K is so that this line could still go up to 5 volts and down to 0 volts with this. So it's like the circuit isn't even affecting these two lines here, okay? And I have this identical circuit for both the clock and data lines. So it's kind of like a sniffing circuit, I guess. So it's like it's not even there, but it's monitoring the two lines. So hopefully that makes sense. It's kind of small on there, but hopefully that all makes sense. That's how to bit bang the I2C data bus using push buttons. Explanation, probably a long and pretty boring video, but if you're still with me, thanks for watching.